All right, our next unit is on vectors. Some of you may have had vectors a little bit before in a science class or something. A vector, we've mentioned the term scalar before. A scalar means it just has one component. Like a scalar just has magnitude, just its length. A vector has magnitude and direction. Magnitude is usually thought of as the length of the vector. The direction is whatever angle the vector makes. So a vector has magnitude and direction. Now you can think of a vector sort of like a ray that you did before in geometry, except the vector actually ends at the arrow part of the ray. It doesn't keep going forever. The point where the vector starts is called the initial point. Where it ends is called the terminal point, because terminal means end. So one of the first things you do with a vector is if they give you these 2 points, the initial point and the terminal point, and ask you to write it in component form. Okay, to write it in component form, all you do is, and it's written like this with these kind of symbols on the outside. In component form, for the horizontal component, you subtract the x coordinates. You always take terminal minus initial. So if the initial point is x1, y1, and the terminal point is x2, y2, then for the horizontal we take x2 minus x1. For b we take y2 minus y1. So that's component form. So like down here, if I said find the component of a vector with initial point 3, 2 and terminal point 6, 4. Well, to find the component form, we're going to take x2 minus x1, so that's 6 minus 3, because that's terminal minus initial, and y2 minus y1, which is 4 minus 1. So in component form, this would be 3, 3. Sorry, that's 4 minus 2. That'd be 3, 2, excuse me. So that's the component form. Now, sometimes they'll write it in something called IJ form. It's really nothing tricky. All they do is take these 2 components, and I is the horizontal component, so that would be 3I plus 2J. That's the same thing. That's all IJ form is, 3I plus 2J. If I had one like this that said, if U is 3, 2, and V is 1, 4, find 2U plus V. So for 2U, this is like scalar multiplication that we did before with matrices. So we take U times 2, so that'd be 6, 4, plus V, which is 1, 4, so that would be 6 plus 1 is 7, 4 plus 4 is 8. Now when it says draw it, if we think of that, when you draw 2U plus V, what you want to do is, like here, if I said U is 3, 2, so that'd be, if I start here, that means U is right 3 and up 2. So there's U right there. Now we want 2U, so we do that again. From right there, go right 3 and up 2. So there's 2U right there. Now we're going to add V, that's 1, 4, so we go right 1 and up 1, 2, 3, 4. So that would be right there, so there's V. So that's 2U plus V. Now, and we'll talk about this next, when you add vectors together, this is called the resultant. So you start where the first vector started and end where the last vector ended. That's called the resultant. So whenever you add vectors together, it's a resultant. Like for example here, if I gave you these are my 2 vectors here, U and V. If I said U plus V, well, I draw U, here's U right here. And then right here at the end, I draw V. So if I start at the beginning and go to the end, so across here, that's U plus V, that's the resultant. So the resultant is what you get when you add 2 vectors. This method where we draw one vector and then start there and draw the next vector, that's called tip to tail. Because we started the tip of the new vector at the tail of the first vector. In like a physics class and stuff, this is almost always what they would do, tip to tail. Now sometimes it works in some math things to draw a parallelogram instead. What you do is start both vectors from the same spot. So if I start right here and I draw vector U here, and start at that same spot and draw V. Now I'm going to make a parallelogram. So if this is U, the opposite side is U. It's equal and parallel in a parallelogram. Then if this is V, opposite it is another V. Well, if I draw that parallelogram, now this diagonal, and you have to remember a parallelogram, the two diagonals aren't the same on most parallelograms. So if I start at that first point and draw this diagonal, that's U plus V. That should be the same as if we did the tail. Sometimes that works better in some math problems to draw it that way, but either way is fine. We mentioned that a vector is magnitude and direction. For magnitude, this is the symbol for magnitude here. It's kind of like, I see some books use a single absolute value sign, but most of them use a double absolute value sign. So if you see that double absolute value sign, that means the magnitude of V, so the length of V. This goes back to the Pythagorean theorem. The magnitude is the square root of a squared plus b squared. The direction, this goes back to what we did in trig. If we draw a triangle, like if we were doing this one right here, find the magnitude and direction for U. This is the one we did before. So U is 3, 2. Well, if I draw that, that means right 3, up 2. So here's that vector U right here. Well, you can see if we draw that triangle, this side is 3 and this side is 2. If we were finding the hypotenuse, wouldn't we take the square root of 3 squared plus 2 squared? Well, that's the magnitude. So to find the magnitude, you just take, once you have it in component form, you just take the square root of a squared plus b squared. So that would be what? The square root of 13 for the magnitude of that one. Now for the direction, if we looked at that picture, like the direction is this angle right here. That's our direction if we call that theta. Well, we know the opposite side, we know the adjacent side. Doesn't that sound like tangent? So we have tangent of theta equals opposite over adjacent. Remember doing that before. To solve for theta, we do the inverse tangent. So you would do that on your calculator. Here, if I want to make sure that I'm in degrees, now we just do second tangent of 2/3. We get 33.69 degrees. So that's our magnitude. So our magnitude is the square root of 13. Our direction is 33.69 degrees. Back to drawing them here. This is 3u minus 2v. So if we started off with 3u, so we have u, remember u, we're going to go right 3 and up 2. That's 1u, go right 3 and up 2, that's 2u. And go right 3 and up 2, that's 3u. So there's 3u right there. Now when it says minus 2v, that means we make our vector go backwards. So vector v was 1, 4, that was right 1 and up 4. We're going to go left 1 and down 4. So there's a negative v right there. V was 1, 4. So a negative v would be negative 1, negative 4. So from here we do that again. Left 1, down 1, 2, 3, 4. There's another negative v. So this would be our resultant 3u minus 2v. We could figure that point. 3u would be 3 times 3, 2. Minus 2v would be 2 times 1, 4. Well, that would be 9, 6 would be that component form. Minus 2, 8 would be that one. Well, 9 minus 2 is 7. 6 minus 8 is negative 2. If I wanted the magnitude and direction of this one, well, the magnitude, so the magnitude of 3u minus 2v would be the square root of 7 squared plus negative 2 squared. That'd be 49 plus 4, square root of 53. the direction, we have the tangent of theta equals b over a, that's negative 2 over 7. So theta equals the inverse tangent of negative 2 over 7. Again, we do that on our calculator. Second tangent of negative 2 divided by 7, you get negative 15.945 degrees. So once you have component form, pretty simple to find magnitude and direction. The next thing is a unit vector. A unit vector is a vector that has a magnitude of 1. So its length is 1, which that's where the term unit came in there, for 1. To find a unit vector, you take the component form. It's hard to see this right here, but you take the component form, so here that's AB, and you divide it by the magnitude of V, by the magnitude of your vector. Like here, if we're finding the component form for U, we're going to take U, which was 3, 2, and we're going to divide it by our magnitude, which was the square root of 13. So that would give us 3 over the square root of 13, comma 2 over the square root of 13. That would be our unit vector. If we found the magnitude of this, it would work out to be 1. Now, we can use this a lot for vector problems, of course. Here you have a plane going due north at 300 miles per hour. So if I drew a picture of that, it's going due north, so it's going straight north at 300 miles per hour. Let's give myself a little more room here. So it's going straight north at 300 miles per hour. There's a wind blowing in a direction of north 30 degrees east. So if I start down here, this is north because we're going north anyway. East is to the right, so 30 degrees east. Here's our wind, and it's 40 miles per hour. Or if you did tip to tail, you would start right here and go 30 degrees east. So this angle right here would be 30 degrees east. There'd our wind to be 40. So if we draw that, if I draw my parallelogram here, that diagonal right there, that resultant, that is the actual path of the plane. You can do this a couple different ways, but here, for component form, you want to break this down to its component. The component form means each vector has a horizontal component, so what part of it goes horizontally, and a vertical component. The horizontal component would be like, let's say you had a rope attached to a box and you're pulling it across the floor. If you have the rope at an angle, part of your pull is pulling the box along the floor. That's the horizontal component. But if the rope is at an angle, part of your pull is kind of lifting up on the box a little bit. That's your vertical component. Well, to find the horizontal component, you take the magnitude of the vector times the cosine of the angle. To find the vertical component, you take the magnitude of the vector times the sine of the angle. So if we're finding component form without the endpoints, that's when you would use that to find the horizontal and vertical component. So here we want to convert each one of them to component form. There's different ways you can do this. Like here, since we both measured from north, you could measure this from north. So if I was going from north, well, the plane, so this would be its airspeed is 300 miles per hour at 0 degrees, because if we're measuring from north and it's going north, it's 0. The wind would be 40 miles per hour at 40 degrees from north. So if we put that in component form for the plane, remember component form, the horizontal is the magnitude times the cosine of theta. So for the plane, so this would be its airspeed, The component form would be 300 cosine of 0, comma 300 sine of 0. The wind, its magnitude is 40, so that'd be 40 cosine of 30 degrees, 40 sine of 30 degrees. That would be the component form from north. Well, now if we work that out, let's see. If you remember from trig, the cosine of 0 is 1, so that'd be 300 times 1. The sine of 0 is 0, so that'd be 300 times 0, so that would be that one. Now again, if you remember from trig, the cosine of 30 is radical 3 over 2. So 40 times radical 3 over 2, and you could just do this on your calculator. That'd be 20 radical 3 if you were doing it by hand. The sine of 30 is 1/2, so 40 times 1/2 is 20. So in component form, that's your two vectors. Now we just add those together. To find the resultant, we're just adding those together. Well, if I take 300 plus 20 times the square root of 3, I get 334.641. And here, 0 plus 20 is just 20. So that's my resultant. So when you add the vectors, that's what we get. Now if we want to find the magnitude, we take the square root of 334.64 squared plus 20 squared. So on your calculator, I still have that on there, so I'm just going to hit squared to square that, plus 20 squared, and I get that. Well, we want the square root of that answer. So it's like 335.2 miles per hour. Now, if you think of that answer, does that sound reasonable? The plane was set to go 300 miles an hour. If you look at it, isn't the wind kind of pushing it just a little bit? So would it make sense that it's going a little faster than what they thought? If they were trying to go 300 and the wind's going a little farther? For the direction, we know we have the tangent of theta equals 20 over 334.64. So theta is the inverse tangent of that. So if I take the inverse tangent of 20 divided by 334.64, I get 3.42 degrees. So that in direction, that would be north 3.42 degrees east. So even though the plane was headed due north originally, it's going to be blown a little bit to the east, so it's just barely to the east. Now that's how I would do this. You see a lot of times in problems, they'll measure from standard position. If you thought of that from standard, remember standard is to the right. So we would have to change all those angles to be from the right. So now the plane would be 300. Well, now from the right, that's a 90-degree angle. So cosine 90 and then 300 sine of 90. The wind would be 40. Well, if that's 30 degrees up there, this is going to be 60 degrees. So that's how you would set it up if you were going from the right, from standard position. If you did all that, everything would work out the same. Your magnitude would work out the exactly same. The only difference would be for theta. When you do the tangent of theta, well, now it's going to be 334.6 over 20. Well, it works out to 86.58 degrees. Well, remember that's from east. Well, if you went 86.58 degrees, if you subtract that from 90, isn't that 3.42 degrees from north? So it's the same thing, just from a different perspective. But you see them do it that way a lot of times in a book. They'll go from standard position. But either one works. This is kind of going back a step. Find the horizontal and vertical components of this. Remember we said for the horizontal component, you take the magnitude times the sine of theta. So that would be 50 sine of 120. For the vertical component, you take the magnitude, I forgot to change those, times the cosine. I'm sorry, I did that wrong. That should have been cosine for horizontal. Sorry about that. This would be 50 sine of 120. Let me go back over that again. I got ahead of myself. Remember, the horizontal component is the magnitude times the cosine of theta, and the vertical component is the magnitude times the sine of theta. So the vertical component, or the horizontal component here, would be 50 times the cosine of 120. The vertical component would be 50 times the sine of 120. You could do this with a calculator or by hand. 120, well, that's a 60-degree angle in the second quadrant. The cosine of 60 is 1/2, so that's a negative 1/2. So that's a negative 25. The sine of 120, that's a 60-degree angle in the second quadrant. The sine of that is radical 3 over 2. So 50 times radical 3 over 2 is 25 radical 3. And you could just do that on your calculator. So in component form, that'd be negative 25. If you took 25 times the square root of 3, that's approximately 43.3. Here, the magnitude and direction for 3i minus 3j. Well, that's the same. Remember, in component form, that's the same as 3 negative 3. It's the same thing. So the magnitude equals the square root of a squared plus b squared. So that's 18. So the square root of 18, or that's the same as 3 radical 2. For the direction, we have tangent of theta equals b over a. So the inverse, so theta equals the inverse tangent of negative 3 over 3. Well, the inverse tangent of negative 1 is a negative 45 degrees. Or if you did that from north, that'd be 315 degrees. So that's the intro